The main theme of this talk is counting semi-magic squares. We begin with the definition. A square matrix M is called a semi-magic square if the entries are non-negative integers and the line sums along any row or column agree. Okay, so here, line sum for a row or column, we just take that row or column and add up all its entries. Now, this will be a variation on the old problem of counting traditional magic squares. We'll also want a diagonal condition. The story here begins in 1916 when McMahon considered the 3x3 case. So here, if I fix a non-negative integer r, the problem is to count the number of semi-magic squares with line sum r. And then for the notation, this count's given by a capital H. The subscript denotes the size of the matrix. The R denotes the line sum. Worth mentioning, this problem shows up a few times in Stanley's enumerative combinatorics 1. Let's consider some motivated examples. More or less, these are going to be the only examples I actually consider. We begin with permutation matrices. So here we have a matrix full of zeros except for exactly 1, 1 in each row and column. For instance, for the 3x3 case, we have 6 permutation matrices. Okay, we'll denote each of these abstractly with cycle notation. And then we also note for 3x3s, these are the only semi-magic squares with line sum equal to 1. Another example, we have circulant matrices. So these are going to be matrices which are constant on diagonals going to the right if we allow for wrapping around. And so for instance, for this example here, we see we have line sum equal to 6 in all directions. Variation, I also want circulant but going along left diagonals. And so here in this example, we see along any row or column, we sum up to 15. Now let's consider the counting problem for the 3x3 case. The formula I want to use, okay, so here we're counting 3x3 semi-magic squares with line sum r. This formula, it's not McMahon's original formula. There are a few variations. They all lead to the same generating function. And then this one's good for a quick talk. Now our outline, okay, we start by noting the sum of 2 semi-magic squares is again a semi-magic square. The permutation matrices then are going to span the 3x3 semi-magic squares under addition. Okay, and so we note span because there's going to be a dependence relation, but essentially there's only one, which is going to be the sum of these 3 permutation matrices equal the sum of these 3 permutation matrices. And then essentially that's it. Now, we want to move this to a more comfortable model. So what I'm going to do is, if I represent a semi-magic square M as a linear combination in permutation matrices, okay, the x's are just going to be non-negative integers. We know that the line sum is just going to be given by the sum of those non-negative integers. And then I could pass from my semi-magic square to a 6-tuple. Now, this representation might not be unique because I can always shift the first 3 ones to the second 3 ones and back and forth. To get unique representation, well, that just means I could take 3 ones and keep moving them from the last 3 to the first 3 until a 0 appears. And then that's going to give me a unique representation. So the thing we want to count, I want to count 6 tuples of non-negative integers. Okay, they should sum up to r. And in the last 3 entries, at least one of them should be a 0. For the count, if I count all 6 tuples that sum to R, well, this is just multi-set counting. We're putting R balls in 6 boxes. So that gives us the R plus 5, choose 5. And then to guarantee the 0 condition, what we're going to do is throw away everything that violates the 0 condition. Now to do that, what we're going to do is I'm going to take all 6 tuples that sum to R minus 3. I'm going to take the remaining 3 and put them in the last 3 entries. So this is going to guarantee that I can't get a 0 there, and so that's going to be discarded. That'll give us, again doing the multi-set counting, the R plus 2, choose 5. And then that's our formula for counting 3 by 3 semi-magic squares with line sum equal to R. Another step, and then we can get to the generating function, which has this extremely nice, compelling form, 1 minus x cubed over 1 minus x quantity to the 6th power. Here's a good place for some points of background. First, what's the interest in semi-magic squares from representation theory? My usual subject. Well, there's a general machinery that comes under a couple different languages. In representation theory, we have these gadgets called Clebsch-Gordan coefficients. So these solve certain classes of tensor product problems. And in the most basic case, the 3 by 3 semi-magic squares parameterize their domain space. In the language of quantum mechanics, okay, these Clebsch-Gordan coefficients solve certain problems on the coupling of angular momentum, particles. This goes back to the 50s, where the jargon would be Reggie symbols or Reggie symmetries. And I'm always amazed that Reggie was able to make this leap from the mess of quantum numbers to 3 by 3 semi-magic squares. If you do analysis or differential equations, okay, this would fall under the umbrella of spherical harmonics. Point 2, okay, so I'm not really an expert on these things, so I can only say so much. So let's note some highlights about H sub n when n is greater than 3. First, we have the Anand-Damir-Gupta conjecture from 1966. So this was improved on and proved by Stanley in 1973. This doesn't give a precise formula for H sub n, but it does narrow down some of the properties of it. So we have the H sub n is a polynomial of degree n minus 1 squared. We have a class of zeros for H sub n that depend on n. So there's n minus 1 of these on negative integers. And then we have the symmetry relation, which is reflecting combinatorial reciprocity. Again, above my pay grade. We also have, so 2008, the generating function for H sub n is known. So that's by De Loera, Liu, and Yoshida. And my understanding is, while it's there, it's tough to use. And so what I've heard is, if you want efficient computing of H sub n, we have that up to n equal to 9, whatever that means. Now let's consider a wider approach. So I'm going to expand our definition so that we'll be able to apply methods from algebra, in particular, Wedderburn's theorem on algebras, and characters from representation theory. New definition. So now I have semi-magic matrices. These are just going to be semi-magic squares, but now the coefficients can be in a field. So let's consider these over the complex numbers for definiteness sake. And then we'll collect all of them together. So for notation, MMN, that'll be the vector space of all semi-magic matrices of size n. Because I have a vector space, okay, first thing we can do is consider the dimension. So if we put down a representative matrix of size n, okay, we'll partition this way. So I have an n minus 1 block in the upper left. We have these strips of size 1 by n or n by 1 left over. Because we're over a vector space, we could let the values in this block be whatever we want, And then once we decide on the line sum, that'll fix the values in the strips. So that means for dimension, I've got n minus 1 squared from this block, and then the line sum is going to fix the other values. And so we get our dimension as follows. Okay, this will be suggestive of something coming up. Now, if I want to have a little bit more idea of what can go in here, well, one thing I can do is just consider the line sum equal to 0. That's going to be subspace of dimension n minus 1 squared, and it's straightforward to find a basis for this. I could just put a single 1 anywhere I want in the block, zeros elsewhere in the block, and then I could fill out so that we get line sum 0 with minus 1s in the strips, and then that'll force a 1 in the other corner. And so this is obviously going to be linearly independent as we range over the different entries in the block, giving us n minus 1 squared. That only gives us room for one more basis vector, and so you could use the identity matrix, but the matrix of all 1s is going to be a little bit more interesting for what comes up. In addition to linear properties, Semimagic matrices also multiply, which is not obvious at a glance. To show this cleanly, instead of appealing to permutation matrices, we instead reformulate the line sum properties as eigenvector properties. We fix E equal to the n vector with all 1s, and then the line sum property along the rows, okay, that we say as row stochastic with line sum R. If I multiply m times E, we get R times E. Okay, and so multiplying by E just sums up along your rows. Likewise, if we want to sum along the columns, I just take the transpose of M and then multiply by E also. Now, with that, okay, we have, if I have M1 and M2, semi-magic matrices of the same size, line sums R1 and R2, if we take their product, we have the semi-magic matrix property with line sum R1 times R2, which is as good as you could hope. Now, what do I do? If I take M1 times M2 times E, well, eigenvector property gives us R2 times E, and then when M1 passes through, we get the R1, R2 times E. Likewise, for the columns, if we transpose, we just switch the order, but then we're going to get the same product when we get to the end. So these multiply. Worth noting, this line sum, it's a linear functional, but not only is it additive, it's also multiplicative, and so we call that a linear character. To identify the algebra structure, we'll just note that MMN is semi-simple over C. Okay, and that just means the radical is equal to 0. That lets us invoke Wedderburn's theorem. Okay, and that says if we have a semi-simple algebra over C, there's some basis for our algebra which lets it be put into block diagonal form, where each block down the diagonal is a full matrix algebra over C. So n by n matrices. Certainly, these blocks are each simple. Now, if we want to count the number of blocks, we just count the dimension of the center of the algebra, since each block contributes its identity matrix. In the case of MMN, we'll see that the dimension of the center is exactly equal to 2. Now, for that, let's suppose we have an M in the center. That means it has to commute with every permutation matrix, or if we conjugate by a permutation matrix, we have to be unchanged. What does conjugation by a permutation matrix do? Well, we're not taking linear combinations of elements here, at least not proper. We're just shuffling the entries around the grid with 2 orbits, on the diagonal and off the diagonal. So if M is going to be unchanged under all of these, then we have to have constant values along the diagonal and constant values off of the diagonal, which means we're looking at a linear combination of the identity and my U matrix, which consists of all ones. Now, we could either run the argument backwards, or we could just compute that U is in the center directly. Either way, we have that the center of MMN is in the span of the identity matrix in U. That means MMN has two blocks using the Wedderburn theorem. We have a one-dimensional subalgebra generated by U. We have n by 1 by n by 1 subalgebra generated by the Semimagic matrices with line sum 0. And I note, if we check that, if I multiply U by M, Semimagic matrix on either side, we just get back U times the line sum of M. So if we multiply an element in here with an element in here, we get 0, which is exactly what we want when we're in this decomposition. So that's an orthogonal direct sum of algebras. Now, to move further, I want to bring in some gadgets from representation theory. The first is going to be group algebra with a finite group. And so for here, it's going to be for S sub n. Later, we'll change it to dihedral groups. So how does this work? Well, what we'll do, for a vector space, we're going to start with a formal basis. So for each element of the group, we're just going to have a basis vector. And then for general vectors, we're just going to take linear combinations. So that means the dimension of this group algebra for S sub n is going to be n factorial. To be an algebra, we want to multiply. And so we'll multiply as we would think. We just multiply the indices. And then for linear combinations, we extend linearly. We note, as an algebra, this is semi-simple. So we can invoke the Wedderburn theorem. This will be block diagonal. And then, if I want to know how many blocks that we have, we go look at the center. In this case, it's a straightforward exercise to show that the center here, well, it's going to pick up a dimension for each conjugacy class. And then what you do is you take the formal elements for your conjugacy class and just take their sum. To tie things together, we have a natural homomorphism of algebras. What we do for each element in the group algebra, say realized as a linear combination, we're just going to replace the formal basis vectors with their corresponding permutation matrices. This is an algebra homomorphism. It's surjective. And so that means, as algebras, I could identify MMN as a quotient of the group algebra by the kernel of this map. How we proceed depends on how big is the kernel. Looking at S3, so here's the picture of what's happening with the algebras. This is 6-dimensional, 1, 1, 2 by 2 blocks. This is 5-dimensional, a 1 and a 2 by 2 block. So in this map, the kernel is going to be 1-dimensional. What's that kernel going to be? Well, we note this is going to be given by, okay, we're going to take the sum of the even elements, subtract off the odd elements. And you'll note this is precisely our dependence relation from earlier on. Once we set it equal to 0 and do the replacement. Now, there's a little bit more going on here. If I note, what I'm doing is taking an average of our formal basis vectors weighted by the sign homomorphism. And so that's going to be key for what we can do in the remaining couple of minutes. So what I note is the sign is a character of S sub n. And so that just means this is going to be a homomorphism into the invertible complex numbers. So I would call this a one-dimensional representation. For a general finite group G, the characters correspond precisely to the one-dimensional subalgebras of the group algebra. And we get that by just averaging the formal basis elements against the character values. Now, this suggests if we want to continue doing what we were doing, we'd like situations where the kernel is built precisely out of characters. If I go to S4, we still have the sign character in the kernel, but then we're going to pick up bigger pieces. So a 2x2 block and a 3x3 block. So that's not the natural direction to go to with what we've set up. What we should do is change the group that we're looking at. And so for here, I'm going to consider dihedral groups, finally. For notation, we'll use d sub 2n. The 2n corresponds to the number of elements in the group. The group elements are the symmetries of a regular n-gon. I'll orient our regular n-gon as follows. Okay, so here we have a pentagon. If we're in odd order, I'm going to want to make sure the middle value lands on the negative x-axis. Now, we have two types of elements here. We have the rotations. There's n of those. And so if we use the cycle 1 through n to denote the generator, that's going to be circulant to the right, as will all of its powers. For the n reflections, okay, with our labeling as so, complex conjugation, okay, reflection across the x-axis is going to be circulant to the left, as will all of the other reflections. Because these permutation matrices form a group, they generate a subalgebra of MMN, which we'll call Dn. Let's return to characters. In general, okay, characters are homomorphism into C star, which is abelian, which means characters have to factor through the abelianization of the group. Okay, so that's just G mod the commutator subgroup of G. Turns out this also counts the number of characters for G. And in the case of dihedral groups, okay, so in n is odd, there are two characters. We'll have the trivial and we'll have the determinant for the two-dimensional realization. So rotations go to 1, reflections go to -1. And when n is even, we'll have 4 characters. So we'll have the trivial, the determinant, the sign on the permutations, and then the product of determinant and sign. We return to our map phi. So here we're going from the group algebra to Dn. Splits into two cases. When n is odd, the kernel of this map is one-dimensional. Okay, that's just the one-dimensional subalgebra associated to determinant. And that gives us a single relation among the permutation matrices. So that's the sum of the permutation matrices associated to rotations equal the sum of the permutation matrices associated to reflections. Now let's return to the original problem. I want to count semi-magic squares, so non-negative integer coefficients, in Dn with line sum R. We have the same model as before, only now we're working with 2n tuples. For the relation, I can move n1s from the second part to the first part and back. We have our unique representation. That gives our count using multiset counting. And I get the generating function 1 minus x to the n over quantity 1 minus x to the 2n. When n is even, the situation's a little bit more complicated. We'll break into 2 more cases based on the parity of n over 2. But the generating function for both will be the same. We have 1 minus x to the n over 2, quantity squared, over 1 minus x raised to the 2n. I'll note, these formulas are known, so they appear in the work of Bergerath, De Loera, and Omar from 2013, but their methods are completely different. So their work is based around counting integer points and polytopes.